So yeah, back to these slides. We started talking about how to make a vector. It's wonderful. So what is a vector? It's an ADT that responds to these operations, like push back something, give me the size, go somewhere, go to an index and give me the value back so that I may like look at it or change it potentially. That's a thing. And we talked about like what are the member variables that are inside of every vector. And every vector is going to hold on to an array, which is going to live on the heap so that I can like get rid of that one, make a longer one if I need to. It's going to keep track of how many items the user has placed into the vector. It's always just a black box to them. One thing there so far, and then there's always going to be a capacity just for us, the implementers, to keep track of like how many things could I place in that heap array, and the user will be none the wiser. All right. So we talked about like to get the size, like that's our num items. So many things the user's placed in. Push back is the hard one. At's kind of in the middle. It's like just go to that index more or less. So pushback was the hard one sometimes. So if we can, if there is capacity, right? If there's capacity to put one more thing in, then do it. Advance num items, put the thing there. Not horrible, but case 2, that was the hard one, right? If we have 2 things in our capacity is 2, we have already stored 2 things like this blue drawing here, then we have to resize our array on the heap, right? We gotta double our size. That's the right way to do it, at least. We create a new size, 4, I guess, in this case, array on the heap. Copy everything over from the old one. Delete the old one so that we don't leak any memory. We're done with that now. Then you can do all the stuff from case 1. Bring in the new one. Advanced num items. Also make sure to change capacity because that's how we remember how big our heap array is. Arrays don't know their size. Okay? Hopefully it's all coming back to us. And so I drew some pretty pictures, and you will eventually be implementing those pretty pictures. But I want you to think about it now. All right? So yeah, with that in mind, we also talked about just like the idea of an ADT. It's just like some abstract thing. Abstract data type is what it stands for. Data structure is the kind of the opposite of that. A data structure is something concrete where you can draw what it looks like in memory. Okay? So an ADT is just kind of defined in terms of the operations, and this is a cute little picture that kind of makes sense. Like to the user, your ADT, your vector that you're building for them, they can't see inside. They have no idea, right? Whatever's happening, like they can only see the stuff you let them see. But to us, the implementers, right? To us, the implementers, there might be a lot going on, and as long as we keep track of it and like do it right, as long as the user gets their public answers responded in the right way, like we could implement this thing however we like. Okay, so that's the silly example of the difference for the day. And if we're good, I would like to ask you a question. You don't have to write this down anywhere. I'll give you like 2 minutes to discuss. Maybe take out paint and draw on top of this if you'd like. But I just like to get that intuition in your mind for how do you implement a vector. All right, so let's say we've got a vector. This one lives on the stack, so it's a local variable called v. It got initialized. Some things were pushed back. The num items is 2. The capacity is 4. And let's say that I want to call pushback on with 3. So v.pushback 3 to yourself. So 3 is like a parameter. You're getting that number somewhere. Let's call it val. Like what will you do? All right, starting with this picture, draw some stuff. Draw how things change. Convince your neighbors that you're correct after saying hello to them. But take a couple minutes to think about how will this picture change if I were to run this line. Okay, does that make sense? You don't have to tell me, but convince your neighbors that you're correct, and maybe I'll ask for a brave person to let me know. Yes, it is. So please start that. All right, and I'll come around and help. Remember what all those member variables mean. By the way, it was plugged in. Did you want to do something wrong? Another minute or so to discuss. We'll come back. I'm the same in my planning. I think you're probably something one like it's ready. Let's just say that that's just ready. But yeah, that's all right. Any brave souls want to tell me what I should be drawing? What's going to happen? We're all shy today. Let's see. Is the capacity going to change? No. Okay, good. We are still here. Is num items going to change? It is. We're adding a new thing, so it's going to change to 3 because we added a third thing. And then val, of course, is going to go to the index of the old one. So like 2 is actually, before you change it, that's a good hint for implementation stuff. Like that's always going to be the index of where you're going to put the new thing before you increment num items. So really, that kind of the process is the way I would implement is like go to index num items right now, set the thing to be the value that we're trying to push back. Boop, and then increment num items. That's case 1. All right. Does that make sense? Nice. We get that? All right. So this one. Try this one now. Let's say we've added 3 and then 4. Now we're trying to push back 5. So this is the state of memory. Draw what changes. Discuss what changes. I'll give you a little less time now. What needs to happen? Well, I need to know what this looks like on Android. But this is a range that we're building. It's still the same. Yeah. Another few seconds to discuss or draw. Who knows? Oh, I've never had that happen before. Like the timer went off and then it made no sound and went away. But I think that's good enough. All right. What's happening? What are we doing? What will go on in memory? Is capacity changing? This time it is. Nice. All right. So that's the very first thing. We're noticing, oh man, I don't have any room. No, my is equal to capacity. I cannot shove one more thing anywhere. So the next step is to take our heap array and make a bigger one. What size? 8. Double the one that we had before. That's going to be the setup, the standard setup. I guess let me try to draw that down here, not in the arrow, but I don't think I can do that very well. So this is going to be our new heap array. And we want to copy everybody over into it from the old one, because like that's going to be storing everything now. 1, 2, 3, 4. And then now we're good to get rid of this one off the heap. It's useless to us now. Chop this guy off, and now the array is this one. Yeah? And now we have room. Now I have room, and the capacity is double. All right, capacity is 8. Now we can go back to case 1 stuff. So, okay, we're adding the val, this 5, to the index 4, which now exists. All is well. Great. We'll put it there and increment num items. I think that was all that we need to do. Does that make no sense? You see it? You think you could implement it? I believe in you. All right, so yeah, with that in mind, now we kind of remember how vectors are going to work. And now we understand the deep down implementation in terms of data structures. So let's try to talk about computational complexity just for a second. We haven't like learned anything serious yet, but some of these words will make sense to us. All right, so let's talk about how fast it's going to take, or how long it's going to take to run these operations. We have size, at, pushback. You can imagine pushback's probably going to take the longest. So, all right, how fast is it to do each of the following, kind of relatively? So, what is size? Dot size is always just like, you ask for the size, it's always num item. Just go there, give the thing back. That's how big the vector is to the user, at least. So that is super fast, like return size, essentially, in the implementation. So that's one line of code. It's always going to be one line of code, even if the size of the vector is 1,000,000, still just that 1,000,000 value is sitting in that int. So we call that constant time, because no matter how big that vector is, it's always going to take one line of code to give back the right answer. All right? So you don't have to remember that word yet. I'll eventually explain it in full, but it kind of makes sense, hopefully. And then .add's pretty much the same. It's like you go to the array, like if you want .add of 2 or something to get this 3 thing back. So if somebody says v.add 2, you're just going to go to the array, use the bracket operation to go to that index that you were asked to go to. So it's again like return R of I or whatever. Question?
So going back to when like the amount of items double, is that something we have to do ourselves, or just do that automatically?
No, there's no magic anymore. You're doing it all yourself. Yeah. Every little piece. So you're getting rid of stuff, delete stuff from the heap, new on the heap again with a new array. Yeah. Other questions? Yeah. So yeah, .add just like go to the array, the current array at the index we want to go to. It's essentially one line of code again. Like go access the array, go to a place in that array, and make it all happen. It's like one line of code where there's like 2 steps, like do the returning and then do the lookup kind of. So, but still, no matter how big that vector is, 1,000,000 things, you're still like going to some index in the blink of an eye. We call that constant time. 2 steps no matter what. All right. We'll make this concrete soon. And then pushback, of course, that's harder. So you can kind of imagine what's going to happen in pushbacks. Like go to the array, put the value there if there's room. If statement, right? If statement, go to the array if there's room. Increment num items, case 1. So it's like 3 things, right, to do in case 1, the easier case. So that is constant time, right? It's always 3 lines of code, no matter how big the vector is. Still, it'll just work. Go to that thing. Go to the index num items, increment. Case 2 is hard, or takes longer. It will finally depend on the size of the vector right now, because if the size is the good power of 2, 1,024, right? If the size is 1,024 for your array, and you're trying to add the 1,025th element, you now must double, right, that thing to make it 2048. 2048 elements, and then you're going to copy in all the old 1024 things, right? And that's going to be a big long loop, and it takes longer time, right, to mess with all that memory than if you were trying to double the size 4 array from here. Yeah. So it takes longer inside the computer. It's got to go through more stuff. So it really depends. It really depends on the size. If you have a larger array, there's more stuff to copy over when you have to resize, because case 2 involves resizing and copying over stuff. We call that linear time. It's the same amount of time as there are elements in the vector right now. It takes just as many. So it's like the graph of y equals n, y equals x. It's the same. So it's like a line. As it gets bigger, more work to do. So yeah, you don't have to understand any of that, but like you've heard the words now. They will make more sense. All right. Interestingly enough, pushback, because of the way we're doing it, because the fact that we are doubling the size each time, and so it's less and less often that we have to resize, on average, if you do the math, pushback is still constant time total across all the pushback operations you will ever do, which is interesting. So it's like you're paying it forward, essentially. Every time you have to resize it, it becomes less and less often. And so on average, it's still like constant time. It's kind of interesting. You'll learn a whole lot about that in like a more advanced algorithms class at a 4-year college, but it's a cool idea. Yeah.
Well, would it be significantly slower to minute by like smaller amounts rather than building it every time?
It would be, yeah, very, very, very inefficient to do it that way. Because imagine you only increased it by 1 each time. It's like, all right, that one, then all right, got to add the new one. I'll just add 1 new one for the new one. 1 new element, like bring that one into that one. And then if you want to add a third thing, like, okay, now make size 3. Add it in. You have to resize and copy things over each time. That's disgusting. See that? So that would take a lot of time, especially as the vector got large. Good question. And then the flip side of that is space complexity. Like, how much memory are we using as we're doing all this stuff? That's another thing we care about in this class. So like, all right, how much memory does it take to do all these things? So like, ask for the size of your vector. Assume you already have the vector saved in memory. How much extra space does it take to like compute all this? Dot size, you got no arguments given to you. You don't have to store those. You're giving back an int to whoever called you, which is the size of that vector. And so it's always going to be, you're returning an int. You're essentially creating an int and copying it back to somebody. That's your num items. And an int is just 4 bytes. So no matter what the size of the vector is, it's constant space. You're always giving back 1 int. That's how much space you're using to do dot size. Dot at, very similar. It's like somebody's giving you an index for dot at. So like you have 1 integer parameter, you got to store that as for the duration of the call. And also you're returning an int. So it's like you're using 2 ints of space at one point in time in your program before they get potentially reclaimed. So that's 8 bytes, no matter how big the vector is. So constant space again. All right. It's always that. And then dot pushback, of course, that one might use some extra space. So case 2, or case 1, you're not doing anything. It's very similar, like dot at, like, okay, go use an if statement, return a value, not a lot, just like a couple ints of space. But for case 2, you have to allocate a brand new array on the heap of size double what you got. Let's say that our current size is capital N. You're going to see that a lot. We use that a lot. It's like our current size is N. You got to allocate an array of size 2N, and then you also are given like the parameter, like what are we pushing back? That's an int that somebody's saving somewhere. You'll have to use some temporary variables maybe, but it's just like it's always the same amount. So it's like two times your current number of elements of int space plus some other constant amount of ints, like 3 or 4 more. All right. So it's still like the graph of this still looks like a line. So we call that linear space. So that one takes a bit more sometimes. All right. So again, you don't have to understand any of this, but we will make all this very, very concrete soon. All right. Are we ready for a different topic? All right, because this is important just to make our lives easier as we're programming fancier things. So I'd like to talk about how to split up like your files. I guess I've shown you that just a little bit. I'll do it some more. Like we'll make a bunch of different files, like a library implementation, header file, main function file that uses the library, just like our lab. And then we'll talk about make files, which automate which automate compilation and like building your program, so that we don't have to just keep typing G++ all the time. So here's kind of where I'm going with this. If you've never learned this before, it's a wonderful, wonderful thing. So let's say we've got a program. It uses 3 CPP files. potentially some header files, but we don't care about them because we don't give those to G++. They're going to get included as they need to get included. All right. And so let's say we've got all these guys, and you compile them like this, right? Give them all to G++. If you don't give a -o something, it's compiled by default to something called a.out, which is an interesting choice that is historical. It's like that creates that. They're all brought together. Yeah, that's how compilation works. All that code's going in there and into machine code form, and now I can run this file. But let's say I change something. I change something in x.cpp. Like, all right, I change a line or two, something quick, something small. With our current knowledge, right, that I've shown you so far in this class, you're just going to use G++ again, and it's going to go through X, which needs to be recompiled, right? And it's also going to go through Y and Z to bring them back into here, yeah? Could you imagine that is going to waste a lot of time if you had a very large project with 1 million different CPP files? Like, then it starts taking hours to compile. Does that make sense? That's a little disgusting. So the question is, if I just change one file, do I have to really like look at the old ones that didn't change and like compile those to machine code again, bring them in? If the answer was yes, I wouldn't be having this slide. So the answer is no, and I'll tell you how. All right. So first we got to go here to this beautiful picture that I stole from a textbook that I don't even use anymore, but it's a wonderful picture. Let's talk about compiling and linking, right? Just so that to make sure we're all on the same page. All right. So the job of a compiler, and these lines get really blurred as like you go in an industry and you talk to people. So like the technical definitions of these are what I'm about to give you on this slide. All right, so the job of a compiler is to translate one program file, one single program file, to machine code or object code, as far as C++ is concerned, at least. So like you have one file, x.cpp, one at a time. So really when you call G++, it's compiling each of these files separately. It's just not showing that to you. All right, so it's like taken one at a time. That's the job of a compiler. All right, G++ is our compiler. All right. It's taken that one file and it's producing machine code or object code, which is the binary format that this processor can understand. It's the translated version of your code. All right. And so that is binary. It's a bunch of ones and zeros. It's pretty. And the standard extension for object code is .o, which you don't get to see if you use G++ like this. It's just like doing it in a temporary place, giving you the final thing. But there's a way to get this. And then once you've made all of your other object code files, like you've made your y.o, you've made your z.o, like G++ will do all that for you secretly under the hood when you say that. And then also you have other things that you're using in your program, right? You're using like cout and cin and iostream, right? Cout, cin, and those all live in iostream. So like there's pre-compiled code as well from the libraries that we're using, like we need those things. To bring it all together and have something that we can finally run to make our like a.out file that we can use the // on, you have to link. So it's the job of the linker at that point. A linker is a program that is very quick to link, that takes all of your other precompiled stuff and the one you just compiled, links it all together into a final executable. All right? That's what you want. Something that you can go and run finally. That's the job of a linker, and of course it's using any library code that's implemented. So unfortunately, the name of the linker is also, G++ is doing it all for us right now, so that's why it's hard to understand this slide. But what's happening secretly when you say G++, all these things, is compiling all of these separately and then linking them together into a final executable file. Okay? That's what's happening secretly, and we can control that. All right? Really, the name of the linker is actually LD. You've probably seen that if you see an error message before. It's called a linker error, like you didn't implement this thing yet. So, but G++ is calling LD for us, so it's a little hard. And so the answer to this question is, of course, no. And the way to fix all this is to get to these .o files ourselves. Get to that intermediate stage so that I can just have y.o and z.o just laying around for me to use. Okay? That's what I want. So here, and I'll show this to you with our old counter class from a previous lecture. So the way that you make this happen, the way that you get at this, is you go to those object files. You go to that machine code file for that just one program, and the way you can ask for that in G++ is you say this -c. Hey, G++, compile it only. All right? You give it one file. It's always going to give you that same name of the file with the .o at the end. Beautiful. All right? And then once you have that, everything works, right? Then you can make just the .o files. You can link them all together, all right? So it'll make that compiled form just that one file, okay? So yeah, let's say you make all those, x.o, y.o, z.o. If you just change x.cpp, you just remake x.o. Keep the old ones for y and z. And then the way that you link is you just give the .o files to G++. So I'm going to show all that to you just right now, okay? So that's beautiful, and that's how it works. And let me show that to you. I'm in the right place, right? Yeah. So, okay, let me copy in, I think it was lecture 2's counter.cpp to here. And all right, I've got it. And I'm going to turn this into a library, our counter library. All right. And so let's make 3 files total. Let's make, we've already got counter.cpp. Let's make a counter.h file that like declares the counter class. This will be helpful for your lab as well. Counter.h. We'll have our header file guards so that we don't infinitely include ourselves. It'll have the declarations of all these things. Boop. Let's see, it'll need vector. And then in a header file, you're never supposed to use namespace standard. So if I want a vector here, I gotta say standard : vector. Because we don't want to force using namespace standard on other people that copy and paste our file when they include it. So we got that. And then, let's see what else. I think there's one other thing in this library, right? Where is it? Get count. It's this guy. This operator less than. That's something that I could be declaring. So let me declare that. And again, it's standard : o stream. Standard : o stream. All right, that's all there. And it lives, this stuff lives though in IOStream. So I better include that. So those are all the things in my library. Counter stuff, the counter class itself, as well as, let's see. I guess by saying friend here, I am declaring this operator. It's already technically a declaration as well. And then we also are declaring this output operator. So everything that could possibly have to do with counters, header file. All right. And then the implementation goes in the CPP file, of course. And I can use namespace standard all day long in that file. And I need to include my header file, counter.h. And that's perfect because that's giving me vectors and IOStream. Like all that's getting included from here. It's taking these, copying and pasting them. That's beautiful. That's perfect. So we got those. And then let's put the main function in a different file, one that just like uses our library. Okay. I'll delete that. And then I'll make a new file called just like main.cpp. I'll put that there. And what I'll do is I will include our counter.h. I will use namespace standard. And that should mostly do it. I honestly don't even need to include IOStream because I'm getting it from counter.h. But if I didn't know that, like it doesn't help. It doesn't hurt to include it twice because it's not going to infinitely include itself. It'll just include it once. And yeah, that's pretty much what we had before, just in different files. So I got main.cpp. I've got counter.h to declare all this stuff. And then we've got counter.cpp to implement all the stuff in the counter class. All right, so does it make sense how I just split up this program into 3 separate files? So now we got a library and a file that uses the library. And I can compile them. So what we knew before, the way to do this is I've got my CPP files. I can give all those to G++, be like G++, counter.cpp, and main.cpp, -o, we'll call it main or something. Like that's the way you can normally do this. Boop, and it runs, and it's happy. But we can make it better, all right? It's better to compile separately so we don't have to be inefficient. All right, so the way that you get at these .o files, you say G++ -c. So here, let's do that. Oh man, why is this unhappy? There it goes. So you'll say G++ -c. So I've got these CPP files. Let me just remove the main file as well. So G++ -c. Put it up here so you guys can all see it. So I've got these files, G++ -c counter.cpp. Enter. There it is. Counter.o. Same for main. There it is. Main.o. Yes, and I will now link them, right? the process to get a final executable, you have to link them. So you give the .o files to G++, you give a -o, whatever you want. So you say G++, give all the .o files, counter.o and main.o, and I'll call the thing main again. And so I've got them all working together. I just linked these two into that one. Okay? So I can now go and whee. And so it's happy. Everything's fine. And that's the way you should be compiling large projects. I hope that makes sense. Because if something changes, you have the old version of the other files that didn't change. You just relink those, and that's super fast. Like compilation, trying to translate that one file into machine code, that's what takes hours if you have a million of them. Linking is just like putting machine code one after the other. That's not hard at all. So that's really fast. So you still have to link everything together when you recompile into new stuff. But that's essentially the setup. If we can just do that every time you compile something, large projects like compile in the blink of an eye. Okay? Does that process make enough sense? It's like go to the dash, use -c, get the .o files for everything. Only recompile what has changed. Like I'll just have to recompile x.cpp. If I change x.cpp, make x.o only, keep the old y.o and z.o, and then link with all that new /old stuff. And that's the process. So like, let's say I change something in main. That's easy. Let's do like, I don't know, C3. Let's print C3 again. I don't know. And so I've only changed at that point. I've only changed main.cpp, so I can keep the old counter.o and recompile into main.o. So d++ -c main.cpp. There's my new main.o, just got made, and now I can relink them. Boop. And then rerun, and I get this printed twice now. Okay, so that's the setup. If we could just do that, everything would be great. This is very tedious, though, right now, isn't it? If you had a million files, that would take forever. So there's a better way, and we get the best of all the worlds. All right, it's called a makefile. So that's where I'm going. So the makefile, a makefile is a wonderful little file that it's its own little language, by the way. It's different to C++, so it's great. It will automate all this for you. Just say once and for all, like give the recipe for how to build your program, and then you're set. You just use the makefile after that. Like it'll always do it right. It'll always compile things in the most efficient way. Okay, so that's what we want. So yeah. This is what a makefile looks like, and it is its own little programming language. A makefile is a file called makefile with no extensions. It's got a capital M in your current directory. It's legitimately called makefile, and it holds little recipes for how your programs get compiled. All right, so here's a bunch of here's what makefiles look like. Number signs for comments. It's a different language. It's like Python. No / for comments there, and then here's a bunch of separate rules to build things. All right, they'll look like that. And let me just kind of walk you through before I explain exactly what's going on here. Like an example rule. Like this is a rule that builds something called main.o. It needs main.cpp to exist first. And then this, by the way, your editor should do this for you, but this is a tab. This is not spaces. You are forced to put a tab right there. All right? A legitimate tab. Oops. Boop. That is a tab. They're all tabs. Like that's the body of the rule. Kind of like Python again, if you've learned Python. So these are all tabs. Your editor should do this properly when you press enter. But then you give it all the terminal commands. These are now terminal commands that you give here. Terminal commands to eventually build that file. Commands. I cannot write properly. Commands to make this all work out. All right, so like this is what you need. So to go from this to this, you use G++ -c essentially, and that will make that. So yeah, these are rules. These are makefile rules. This is a rule. All right, and yeah, what comes after these? So this is terminal commands after you press enter and tab over, and the stuff up here after the colon is the name of your like ingredients for your recipe, for your rule. They're also called requirements. Like I need these things to exist first. Requirements. So like to build the final program, I need main.o and foo.o to exist first, and then I can link them together and make that thing with that same name. It's usually you're making a file with the name of the first thing. Like that's your target, we say. All right, that's my goal. And so that's pretty much a makefile. Let me teach it to you now. All right, so this is the example I like to use in my CSCI 40 class. So let's make a peanut butter and jelly sandwich using makefile rules. All right. So using these ideas, like first is the name of the thing you want, then a colon, then you space separate all the things you need, your ingredients, your requirements. Then you press enter, tab over, and you give step by step all the things you need to do to achieve your final target goal thing from your ingredients. Like you give the recipe. All right. So, okay. How do I make peanut butter and jelly? That's the name of the rule. Colon, to separate all the different ingredients. I need a plate. I need a knife. Right? I need definitely peanut butter, definitely jelly, definitely bread, all these things. You still good? Yeah. And then we tab over, like let's say those are my ingredients. We tab over. And all right, this is something I also like to do in my CSCI 40 class on the very first day. Like, how do we make peanut butter and jelly? Give me the recipe. So like, all right, how do we do it properly? Okay, well, let's go open the peanut butter jar. Like, be as precise as you need to be. Open the peanut butter jar. Open the jelly jar. And then take out 2 slices of bread. Like, whatever you need to do, right? It's in order. This is your little recipe. This is a makefile. This is how it works. And you're writing it down once and for all so that you can rerun these rules automatically. Bread, Eventually you've made it, you close the sandwich, right? Something like that. And the beauty of makefiles is you can have a bunch of rules in one file. And you can give like rules for intermediate things. Like your goal is probably the final program and it needs this thing. But if that thing didn't exist, you can make a rule for that. And it will go looking for it, which is great. That's what we like. So let's say that we didn't have peanut butter. Like, how do you build peanut butter? You can have a rule for that, and it can go looking and build the right thing for you. Like, all right, I need peanuts and a blender, or I need a car and money. And then you go to the store and you buy peanut butter, right? If only I could spell today. But yeah, that's kind of the idea. If you tell the makefile, like, give me this thing, you tell it to give you this final thing that you care about, it'll just go looking through the ingredients, but like, it'll open up the pantry and make sure it has all this stuff. And if it finds something it doesn't have, it'll go looking for a rule to build that. It's very, very nice and efficient and like optimal, okay? So yeah, that's I think what I wanted to say. So in general, again, it's like name of the thing you want, colon, space separate all the requirements on that same line. Those are your ingredients. And so those are like, to us now, on the terminal land and in compiling things land, these are file names. These are things that must exist. All right, so requirements must exist. Must exist before the body of the rule can run. If you don't have those things, it'll either give up saying it can't find them, or it'll go looking for rules to build those before the body of the rule can run. Okay, that's what you want. The name of the thing you want, we call it in makefile land, that's your target. It's your goal. Target. So you'll see that printed to you if you mess up a makefile. And then you tab over, of course, and you give as many terminal commands as you need in order, running one after the other, to take these things that you know you have now. You only hit the body if you only have those things, and then use them to build the thing you want. Okay? So these are now steps. They're terminal commands, though. Steps needed to make the thing. So it has nothing to do with C++. It's like taking files and making other files, essentially. That's what makefiles do, okay? So that's kind of the structure. I'm going to show that to you for a counter example. And once you have it, you can ask your makefile program. Like there's a terminal command called make that goes looking for a makefile and it goes running the rules, all right? So let me show that to you. Let's make a makefile for our stuff. So again, I've just got these guys right now. Let me remove all the compiled files. Get back to blank slate. All right, and let's make a makefile now. Dun, dun, dun. So then I'm gonna make a file legitimately called makefile. That's what it's gonna go looking for. All right. And in makefile land, comments start with number signs. So this is a makefile comment. Yay. And then you give your little rules. So, all right, what do I want? It kind of looks like this. I want the ability to make the things I need right now. So I need like .o files first. So let's make main.o. Main.o. That's the thing I want. That's my target. What must exist in order for me to ever possibly hope to make main.o? Main.cpp, right? Otherwise, there's no point. And then I press enter and automatically tabs over for me. So don't try to press space yourself unless you know that that was a tab character. And then I give all the lines that I need, terminal command lines, to take that ingredient that I know I have now and build the .o file. So it's g++-c, right, on the name of that file. Yeah. So that's a rule. That's a rule that you can run. Same with, what is it? Counter.cpp. Same exact kind of rule. Like I want to build counter.o from counter.cpp. Run that line. Yeah. And then I want my final program as well, like the thing I called main. What must exist in order for those, for main to get made? I want my .o files, right? Main.o should exist, counter.o should exist. And then how do I use those things to build what I want? I say g++, give them, and -o, call the final thing the same name as the target. All right, so that's a makefile. Does that make enough sense? Those are all the rules. That's how you build it. And now we can go ask the make program to look into this file and do it for us. And so here's how you do that. It's a command called make that goes looking for the makefile. You say make space the name of the target you'd like to build right now. All right, that's how you run a makefile. All right, so make space main.o. Boop, goes run the rule. Make space counter.o. Nice. Make main. That's already saving us time, isn't it? That's quite nice. Now it's there. It's runnable. Cool. We can do better than that. Let me remove all. Oh, shoot. Let's remove all the compiled files again. Back to a blank slate. The beauty of make files is this: make main. Hit enter. Do you see how amazing that was? It ran all the other ones too. Like it needed main.o, it didn't have it. I got rid of it. It found the rule. It made it. Isn't that nice? It did the same for counter.o. And now it's like, all right, now I have the things. I can run the thing you really wanted. And so in one fell swoop, I've got main to go and run. All right. If that wasn't cool enough, let me make a change to main.cpp. Print it out again. I've now changed that file. I've changed main.cpp only. I need to only recompile main.o. I can say make main again. And it noticed the change. It's going to efficiently as possible recompile. It notices that counter.o, I can reuse that one, but I need to recompile this one. So remakes main.o, runs the thing to link them all together. And again, I'm happy. So you do it once, you're done. Just keep on reusing it. Isn't that nice? Just say how to build it just once and for all. It'll figure it out. Any questions about that? So that's our makefile.
Files in the same file, they have to like directory.
You can tell the make program, like give it the actual name of the make file if you chose a different name. That's how that could work. You can look at the manual page for the make program. I forget how that is. It's dash something. Make -f. Give the file that is your make file. Yeah, another question.
So if you also just like make one rule that includes main and counter to.cpp, and then g++, those do 3 lines, and then run the third g++ rule.
Yes, but then we'd be back to square one again. Like the whole point of this is to efficiently compile things. If we had a million different CPP files, doing it that way would again take 5 hours. Does that make sense? So we'd like to split it up. We'd really like to split it up. Good questions, though. Any other question? All right. So also, you can get even more shorthand. If you just say make by itself, usually you put the most important rule at the top. So like this one should be at the top. If you just say make by itself, it'll run the first rule. Just like make. That's now equivalent to make main. It's like I don't have to do anything. It's up to date. Nothing has changed. It knows. Cool. It's tracking file modification times. That's the secret. But that's makefiles in a nutshell. There are better, fancier ways to do makefiles, and I might as well just show them to you now. There's like shorthand, little special makefile variables. So let me do that for us. So I'm going to make a new copy of this makefile. Or here, let me copy our current makefile into makefile old. Like that was the original one. You now have it. I'll give that to you. It's in our directory. Go look at that. I'm going to edit this one some more now, though. So here is, let's make it cooler. You can have, let's see. Which order do I want to do this in? There are multiple compilers in C++ land. G++ is the GNU C++ compiler, but if you're on a Mac, the compiler that they prefer there is called Clang++. G++ is just an alias for that, honestly. But we have that installed on the server as well. You can choose which one you want to use. There are two competing C++ compilers. So in the makefile, you can specify and make it very easy for the user to change which kind of compiler they wanted by making a variable. You can define a variable like this using an equal sign, but no spaces. Like people, usually they say this, CXX equals the name of the compiler I want to use, G++, where X is just a sideways plus, I guess. You can't have plus in a variable name. So this is like meant to mean that is the C++ compiler I want to use right now. And then to use that variable, you say, to look it up, you say $, then between parentheses, you put that variable. It's like, that will expand to be G++ now. All right. And so you put it there because now you can change it really quickly. Use the other compiler for everything. So there's that. Let's see here. The name of your target, shorthand for that is $@. So if I want to make this thing called main, that's faster. It's the name of my target. It's like the @ sign kind of looks like a target, right? A little dartboard. So that's that. All of your ingredients, that's $caret, I guess. That's shorthand for every single one of your requirements all at once. So like I want to use all of those to build my target. So like I could have said that. All right. You'll get used to it. And then, all right, same with this one. -C, all of my ingredients. Sometimes you only want the first one. Could have done that as well. That's $less than, like pointing to the left. So there's that. And yeah, this can all be changed into this. And you have options like this. You just want the first one because you could have used this one as well. So those are kind of interchangeable when there's only one ingredient, one requirement. And yeah, so nothing has changed. Like I say, make, like still happy. Everything is exactly as it was before. Like this is legitimately equivalent to this file. Does that make enough sense? Is there a question or is that a stretch? Okay, let's see here. So yeah, that's what's going on. And also, people really like to make a rule, even though it doesn't build a thing. People love to make a rule called clean that just like gets rid of all of your compiled files, get it back to a blank slate. So I like to make one of those too. So it's like clean is its name. It requires nothing. And its job is just to remove every compiled file. So like remove every .o file that I've ever made. So star.o just means every single .o file in the current directory. And then the final executable is called main, so we'll get rid of that too. And if they don't exist, it'll complain, so do -F to not complain, just in case they don't exist yet, or some of them don't. So that's a special kind of rule. This one's not actually building something, it's just like, it's a shorthand for like something I might want to do. So clean doesn't make anything, it just removes all compiled files. So really, there's something I should be doing. You're supposed to mark this as like a phony rule, but I don't want to get into that. It's still going to work. So that's a special kind of rule. I can say make clean, just like delete. Now I'm back to a blank slate. If I say make, that'll run the first rule to make the main program from blank slate land to make everything as it needs to be made. Okay, so yeah, that's just another way to do all that. And that's useful sometimes, like something weird happened. Just go back to a blank slate, please. I think that's all that I want to say about makefiles. Does it make enough sense? I think I'll be giving you every makefile in your labs, but one day in like a test, I might ask you to make a rule or something. So you need to understand it still. All right. So yeah, makefiles, very useful. Use them. All right, I really only have one last thing for the day. I would like to talk about comparison classes if we are ready for another topic. One last topic. Yeah? All right, so let me make a silly looking class so that we can do silly things with it. All right, one day you'll want to do this. So I'm going to make a class called holder. It's just going to hold on to one thing. It's like it has one member variable. It's kind of a wrapper around an int, we'll say. And let's do stuff with it. All right, I'll call it sorting classes.cpp. Oh, man, what's happening? Am I in the wrong? How dare this? What have I done wrong? Maybe it's because I was in sorting underscore classes.cpp. What happened to my fill in the blank? There it goes. I don't know. Cool. So I'm going to make a class called holder. And I was going to hold on to one thing. This is just a silly wrapper around this int x. Every holder object has an x inside of it. Okay? That's how it'll look. And I am going to, I guess, give it a constructor. I'm going to be very lazy and implement everything inside the class like a bad programmer. So let's take the thing, set it, give it a body that's empty, and then we'll have like a getter, get x. It's const, we return x. So there's my silly class implemented all in one go. And let me make some holders. All right, let's be like holder h1. Set the x to 42. Holder h2. Set the x to 55. I don't know. Holder h3. Set the x to 128. So I've got 3 holder objects. They're all holding on to those different values. And I'd now like to do something weird. I'd like to make a vector of holders. Why not? So I can do that. Vector of holders. I have that type. V, and it's going to hold on to, let's do H2, H3, H1. It's a little bit out of order, right? It's going with the 55 one, the 128 one, then the 42 one. And let's say I would really like to sort this vector. Like that might be something you want one day. I would really like to sort this vector, right? We know how to sort things, right? There's a function called sort in the algorithm library. Let's go look at it. Whee. It's probably another, yeah. Where are you? There it is. Sort. On a vector, you give it begin and end. You say sort begin and then dot end to give it the whole thing. So we'll say, all right, sort v dot begin, v dot end, and you can imagine I'm going to get a very disgusting error message right now because it's like you've made your own type, dude, and you're asking me to sort things of that type. That doesn't make any sense to me yet. So here's the disgusting error message. Oh wait, no, sorry. First of all, I need to include the algorithm library. Get a slightly better error message right now. Now sort exists, and now I'll get the good error message. All right. So what it's saying, you scroll up. Again, it's saying all the things it knows how to sort, and holder is not one of those things. So if you look, eventually, you'll see this less than sign. It's like, because what sort is implemented using is nothing but less than, strictly less than. You can get everything from less than if you like do negation and like flip it around, you get greater than, of course. So there's a way to get everything from just less than, and that's what sort is using deep down in the implementation of sort. It's saying, if you were, I don't know how, to take 2 holders and know which one came before another one. Because that's what you need to sort, right? That's what sort's trying to do, and it's like, you made your own type. You got to tell me, dude. I have no clue how to sort holders. I can't just make stuff up. And so that's what it's complaining about. I don't have a less than operation on holders right now. If I did, I could sort this. If you told me how one holder came before another one, then I could put them in order, in your order. Does that make sense? So that's your first option. If you would like to sort your objects of your class as like a vector of them or something, then your first option is like use sort and make a less than operator. You can do that now, can't you? We know how to make operators. Like, all right, option 1. Make an operator less than. All right, let's do that. We have 2 options. We're the implementers of the holder class, so we could implement it inside the class, because like when it calls less than, right, it's going to be like doing something like this: h2 less than h3 in like an if statement. That's what the sort implementation is going to be doing. It's going to do stuff. And so this less than operation will turn into either, right? You're either going to get h2 dot operator less than with h3. It could be a method of the class, or it could be a operator less than function on h2 and h3. Either one, as long as that operator is there somewhere, then it's happy. All right, so let's make it a function outside the class. Let's make it have this one get called. As long as it's there somewhere, it'll work. So all right, what does it mean? Operator less than to tell me if two holders are less, or one holder is less than the other holder. So all right, give me 2 holders. And I'm just going to look at them so I can take them by constant references. A, constant holder reference B. I've got them. What should be the type that a less than operation returns? Do we hear that? It's going to say yes or no, right? Yes, it's less than. No, it's not less than. So that's bool. True or false? And then now we have to come up with, like, how are we going to define one holder being less than another holder? What's that? Yeah, we could definitely do that. We'll use get x, and I guess we'll just compare based on x. Yeah, we'll compare based on x. Like, let's say that one holder is less than the other if the x inside of the holder is less than the other x inside of the other holder. Yeah, that would be a normal way to compare them. But you could compare them, like you could say it's less than if they're greater. It's up to you, the programmer. And then it would start to prefer bigger ones rather than smaller ones. So that's the thing. So let's return. This is outside the class, so I've got to use the getter unless I make it a friend. So a.getx, return whether or not a.getx is less than b.getx. Yeah, that would work. And now it will compile. Sort will work. Let's see the fruit of our labor. Let's look at this v now. Let's go through it and print out, like, hey, did it do anything? So for every, let's iterate through with a bunch of constant holder references, h's in v. Go through all of them, call them h. See out h.getx with some spaces in between. Something like that. Oops, I did not mean to go into them. That is going to give me an error. Boop. I can now run it. And look at it. This started out with 55, 128, 42. Now it's 42, 55, 128. It really did sort them. So just adding that less than operator is one option. All right. Does that make enough sense? Because C++, it gets people are sometimes angry at C++ because it gives you a million different ways to do the same thing, and then people get their preferences, and it's a little disgusting because of that. But you also have a lot of power. So there are 2 other options that I want to show you. The other one, the next one, is make a comparison function. It's a little weird to think about. You didn't need to make something called operator less than, because maybe like you want to save that for some kind of like less than comparison, but you want to compare based on another idea of whether or not holders come before other holders. All right. So you can just make a function with a name other than operator less than that works exactly the same, that still returns true or false. It's going to take 2 holders and returns true when the first should come before the second, right? Because it's essentially you're having a function stand in for less than. All right. But again, you can change the definition of less than, which may be a little philosophical and weird, but that's the thing. So just make a comparison function that returns true when the first thing that you got, your first argument holder, was supposed to come before in sorted order the other one. Okay, so that's option 2. Let me comment out that one. So that's option 1. Option 2 is make a comparison function. And that is, it's honestly here, right? It's actually showing you that you could do that. Sort from begin to end using this function. Just pass along its name only, and it'll call it for you. So how, yeah, it's called a compare thing. That's the secret third argument, if you look at that. But yeah, the example is helpful. So let's do that. Oops. Let's make a comparison function. I'll call it, I don't know. It's going to look very similar to this. It's going to take two holders, say when one should come before the other. It's just got a different name. We'll call it holder compare. Let's say that under this function, let's define one holder, like the first holder A should come before the second holder B if, I don't know, A's X is bigger this time. That could be a definition of should come before, right? It doesn't have to be less than, because it's not less than. It's got a different name, right? Holder compare is its name now. And so I can call that. I can say sort, please, the entire vector from begin to end using holder compare. Yeah. And then I'll print out the resulting vector. And now it's sorted in descending order because it preferred bigger x's, didn't it? Does that make sense? That's cool. It's the definition, right? We've defined what it means for one holder to come before another. It could be any order you care about, okay? We ready for the last way? Last way is the most disgusting. Probably we'll never want to do it this way, but you can, right? You can next, the final option is you can make what's called a comparison class. Right? Another word for that is functor in C++. That's a very overloaded term. Does not mean that in mathematics, sadly. But a comparison class is a class that has the operator parenthesis implemented. So that means if this is implemented, if you implement something with this name on your inside of your class, that means you can call your object like it was a function. Because that's what it means to use that operator, right? It looks like a function call. Weird. And so that, then you just implement that. It's a separate class, and that inside this should take two holders if that's what we're trying to compare. And again, returning true when the first should come before the second. So that's very, very weird, but it's a thing. So let me show that to you. Dun -dun. So this is the most clunky of your options, but it's a little, people use it. So I need to make a class, a comparison class for holders. It's called holder comparison class, I guess. All right. And then public, you got the only thing that needs to be in it is operator, bool operator, parenthesis. That takes two holders. I'll take them by constant reference because I don't need to touch them, just look at them. And again, I could return something like when does one come before the other? So like we'll do this one again. That is called a comparison class. All right. And sorry, no, it's operator parenthesis, excuse me. It looks so weird, I typed it wrong the first time. And that needs a semicolon. That's a little weird looking. You have two sets of parentheses, like that's the name of the operator, and then here are its arguments. Here are its parameters. So we could use that. That's option 3. Option 3, comparison class. Essentially, we're going to call sort in the same way, but we're going to pass an object of this type. And then it can just call it. Because at that point, for all intents and purposes, it works like a function. Let me show that to you. It's very weird. So I'm going to make an object of that type, holder comparison class, HC or whatever. And then I can sort with that. Sort, begin, end with HC, that object. And remember what it's doing. It's doing something very weird. It's got that going on right there. Operator parenthesis. And again, it'll work in a weird way. So let me show you like what HC is doing. We've overloaded this operator, the function call operator, which means HC, you can treat it like a function right now. It's like cout, HC is its name. It has an operator called parenthesis. You can call it like a function. Does that make sense? And I'll give back true or false. H1 is less than H2, so true. So that's what it's going to do inside of sort. It's like calling it like a function. Just like this other one. Like we pass this function and it calls that one because it really is a function. But like you can give something that isn't a function as long as it can be called like one with this operator. Isn't that weird? So that's a little odd, but it still works. Any questions about that? Now you'll at least understand if you ever see that. Yeah, let's comparison class. Technically there's a secret option 4 if you want to go there. Let me show that to you. Dun, dun, dun. I'm not going to test you on this one at all, but there's something called a lambda functions in C++, if you've heard of those. Secret option for an anonymous function. Because like usually you want the best of all the worlds. Like it's kind of clunky to make, like this one makes a lot of sense. Like you want to compare based on some special comparison function, but I'm only ever going to use that special comparison function on this line, so it's kind of silly to like make it right there. It's polluting the namespace, we say. It's like it's just an extra name laying around there for one purpose. So your secret option 4 is you can say sort v begin v end using a function that you can write on the fly called a lambda function. So you give that, then you start giving the implementation. Const holder reference A, const holder reference B, and then you give the body right here. It's like return whether or not, let me just steal it from up here so I don't mess it up. That's the body of it. And so you just like, or it's really this function, but you get the idea. Let's do the less than one. Like give it the body right there. Whee. And so this is called an anonymous function. I'm making a function on the fly. Let me zoom out so you can see it all. And I'm sorting based on that. And here is the function I want you to use to sort. It doesn't have a name. It's called an anonymous function. It has no name at all, but like that's its implementation. It takes 2 holders, returns that based on them. Implementation within an implementation, which is fun to think about. So that will also do the same thing. I'll show that to you. Sorry, it's so small I gotta show it to you all in one line. But it'll work. It's still happy as long as you give away, like that's a function all at once. All right, so let's go back to the old one. So I'm not going to test you on this one, but that is an option. All right, so cool. Bunch of different ways to sort your particular kind of objects. Okay, if you put them all together in a vector or something, now you know. I think that's all that I wanted to say. Are there any questions about this or anything else we talked about? All right, because my last job is to give you your next lab for the day. Let's do lab 1. Release. So just like the current one's due tomorrow, the next one will be due next Friday. Let's go look at the write-up. Please make sure to do attendance. I'll stop attendance after I stop explaining all this. So yeah, this one is vectors. Hint, hint, part 1. There's going to be more vector stuff. So you got to get this one down. This is one of the few labs in this class where you got to do the first one to do well on the second one. That comes after. All right. So yeah, we're going to implement vectors together. This is like the simple way. There's more to it, but you will get a working vector by the time you've implemented all this. All right. So you can use, go and do the Gimme Lab 01 at CSCI 41 to get the starter code. I'm going to look at it on my end. Oh wait, do I actually have it here? This is a brand new laptop. I might need to go get it for a second. I don't. Cool. So here, give me 1 second. I want to put it in a special place for myself. GitHub, Lots class, starter. Boop. You don't have to get it in this way, but I'm going to get it in this way for myself. You use Gimme. Boop. Starter code 41. No. Cool. Now I can look at it on my laptop. So here are the files you will get inside of the lab. And let's talk about them. You are going to be implementing, we can't say vector, so I'm going to call it vec, all right? The class will be called vec, and so vec.h is the declaration. which you'll just be looking at and not touching, you're going to be implementing vec.cpp. So here's what it means to be a vector. We've got a constructor, or vec constructor. We've got pushback. It's going to be a vector of integers, yeah. We got size, should be const, right? We've got at goes to a certain index and gives you back a reference to that thing so that you can potentially change it. And then we'll also have sort, because why not? You know how to sort stuff. And then here are your member variables. You got the array itself on the heap, stored as a pointer, right? Some people put the star right here, so I'm just going to give you practice with that. Num items and capacity are all there. And then here's a private method, just for us to help you implement pushbacks case 2, resize. So the user should never be calling that, right? Just for us. But it's nice to have it. And I think you'll use it and like it. Okay? So there's that. And yeah, that's the goal. So for the constructor, like we were saying in my pretty slides, because your job for this lab, go back here, read my pretty slides, right? My pretty pictures, implement the pretty pictures. It's like, this is what the constructor should do. This is what memory should look like. So you want to start your vector out empty, num items be 0, capacity 1, and have a size 1 array of ints on the heap. Yeah, that's what the constructor should do. And all that's happening in vec.cpp. Okay, so there's your constructor, all those things, and then everything else. Okay, just go and implement all the stuff. I've given you some blank stuff. I'm giving you some help in comments. Read those. It's like resize, you should call from pushback. All right, that's the goal. And this is a private method. So the job of resize is like double the thing, copy it all over, get it ready, right? Do the resizing stuff. So the way to call a method on yourself, right? Because like you're in pushback, like I'm in case 2, I better resize. You want to say like me.resize or something, right? There's an equivalent of me, but I haven't taught it to you. You can just say resize. Call that method like a function, because it really is a method, private method. But if you call it like this, that will call resize on yourself. Okay, that's how you'll use that. I did not want to save. I don't think it changed though. Better not have changed. Ah, man. I'll figure this out later. Okay, I think that's what I wanted to say about that. Pushback, you got the cases, dot size. You want to, whenever I've given you something, this is just to make it compile, right? This is obviously wrong. You will delete that line, okay? You'll implement that. And then same with this one, you will delete all of this. It's just to get it to compile. This is a horrible undefined behavior implementation right now. You don't want this. It'll just compile though, all right? But it's got to return, you go into the element, go into the index, find the thing. And then the sort method I've already given to you. Here's how you sort an array. You gotta use pointer arithmetic. Sort the memory starting from here up until, but not including here. All right. So that's sort method done for you, but you'll be doing the rest. All right. Does it look like you expected it to look? Does that make enough sense? That's what you'll be doing. So there's that. And did I really mess with it? Okay, good. And then I've made you a testvec.cpp file. So like, there's your main function, right? To get it working, right? To get it working. And it works hand in hand with this testing library as well. So the testing library has that assert true inside of it. So that's the library that contains that. So that's what the testing library contains, assert true, and its implementation. So like we've got 2 libraries really, the vector library and the testing library, that are going to be used in this testvec.cpp file. Okay? And then, so it's including both of them. And here are my tests so far. I'm making sure that an empty vector is size 0. I'm making sure that, all right, if I push back these things, this is what should happen in memory, right? Just like normal stuff. Slightly more complicated as you go down here, like, okay, this is a very complicated test. I can help you figure it out. And yeah, sorting things. But that's more or less what I'm testing you on originally. So I've got 4 tests. You want to make sure they pass. And the way that you compile this is now through a makefile. I've given you a makefile. So like you could do it yourself if you want, but here it is. I am being very lazy. You could probably update this and do it the right way with separate compilation, but I've given you a lazy makefile. And you just say make. You say make, it'll run the rule. and build this test vec file, or you can say make test vec, either way. All right, and that's the idea. So get my test to pass, like that. I'll give you a runnable thing finally, and get my test to pass, and then I want you to write 4 more tests, please. Same kind of stuff, so like make a function per test, something like that, and call assert true exactly 4 more times, so that passed, like you see passed 8 times total. Okay, that's what I want to see. Does that make enough sense? So implement vec.cbp. Where is all this? Implement vec.cbp using vec.h. You implement all the stuff there. These are your member variables. That's their names. Can't change those. And then get my test to pass, then write 4 of your own. All right. So yeah, I think that is all that I wanted to say. Then you submit. The 2 things that you're submitting is the implementation file and your updated test file. So because you're not submitting the header file, it means you cannot make changes to the header file and expect those to like get into your grade. All right. So you can only mess with the CPP file. That's where you should be changing the vector library stuff. And I think that is all that I wanted to say. So you'll turn that in before the due date. And there will be more to vectors. This is a very important lab. You got to get this one good and 100% so that you can do the part 2 version. All right? Because you'll be copying over this code into that one because there's more to talk about. So I think this will be very satisfying. Like you'll have a vector. You made your own vector, right? It's working the same as the vectors that you've known and loved from CSCI 40. It's really cool. And I think you'll enjoy it a little bit. But I think that's all that I wanted to say for the day. Are there any last questions that should be recorded? All right.